Good evening, everyone. My name is Rajat Bonik. I am from IITSN Dharwad. I am one of the PMI research scholar at IITSN Dharwad, and I am get chance to talk to you or discuss you this ground improvement class, which is already taught by Professor Dilip Kumar Vaidya sir. I am one of his TA at this course. Today is week 12, and this is our by this plan lecture plans. This is our last class, but there is one more extra class will be happening at on Wednesday at 6 p.m. same time. Please join this class. I will discuss here all the 12 weeks very shortly. And if you have any doubts, please ask there. And one and two point I made here, I want to say that these lectures are recorded, and it will be shared by you through Nptel team in my YouTube channel. And also, whatever I am discussing in this class, I will share or material I will share you in Google Drive. You can access it. And also, if I am get disconnected due to some problem, please stay on the line. I will try to join very quickly again, and don't worry about this. So let's start our today's session. So today we are discussing in the uh, in previous week we are discussing about the geosynthetics material, and today is the continuation of this previous week, and we actually select the we actually discuss uh, today's session we actually discuss the lectures of this week 12. Five lectures are there, and one by one I'm discussing. After that, if time permits, I will discuss also one problem in this week. So uh, let's start our session now. I'm sharing my presentation. Please wait. I'm sharing it. Uh, Please wait for this. I think it is visible to everyone. So please wait for a few seconds. I'm adjusting my PPT. Uh, so I think now it is visible to everyone and it is very clear. So let's start our today's session. First, I discussing the previous week lectures very quickly because whatever discussing in week 12, it is the continuation of week 11. So I am briefly discussing the week 11 very shortly. So first, in week 11, we're discussing the introduction of the geosynthetics and what is mainly represent the geosynthetics. So geosynthetics actually the combination of polymer and geomaterial, and by this way we can easily improve our ground by different way, and different function need to be adjusted due to this geosynthetic material, and it is mostly it is very cheap are cost effective. So, by this way, different way. different means we can address different function or different improvement we can done by the geosynthetic material. So there are different types of geosynthetic material we will discuss. These are mostly geogrid, geotextile, geonet, geocomposite, geomembrane. Like this, many others are many other types are there. So we also discussed that what is geogrid. Geogrid is actually geosynthetic formed by the regular networks of tensile element. Actually, most of the geosynthetic material are tensile material, tensile element because we apply this. Geomaterial or geosynthetic material to improve both the tensile strength of the ground. So these are the mostly use these geosynthetic material as a reinforce the earth soil or like this. Then we discuss in the different others just like geosynthetic, geotextile material, geonet material, geocomposite. So no need to discuss again. It is elaborately I am discussing in previous class. And then I will discuss the function. What are the different function we need to address or we need to for this geosynthetic material. Like most importance are these are reinforcement, filtration, separation, drainage, erosion, and barrier protection. These are the different function we use this geosynthetic material. So for reinforcement, we reinforce uh, as a reinforcement. When you use geosynthetic material as a reinforcement, we actually most increase the tensile strength of the ground and also the load distribution capacity of the ground. So So by this way, you can see that figure that without geosynthetic material, the load is concentrated one place. So it is created some damage or crack. So after applying the geosynthetic material as a reinforcement, we actually distribute load over a larger area. So by this way, we increase the strength of the soil and reduce the crack or failure of the surface which is below the this reinforcement. And then also we use as a separator or separation as a geosynthetic material to separate the coarser material from the finer material. And it is mostly used for the pavement. So in pavement, if you know that the pavement thickness is uh, uh, pavement is created by the combination of the coarse aggregate, fine aggregate, like that way, layer by layer, we can create it. So, if the lower layer is mixed with or coarse aggregate, which is governing factor or governing material for this uh, pavement, if it is mixed with the fine aggregate, then the load distribution may not be properly take place. So for this we use the geosynthetic material for separate this coarse aggregate from the fine aggregate. Then we discuss about the geosynthetic material as a filtration. We actually most of the case we use the geosynthetic material below the pavement surface to collect the water and expel away this water from this pavement, and for pavement may get safe from failure due to this water or seepage. Then also we can use this geosynthetic material as a drainage also, and in drainage same way we can expel out the water below this ground surface so that the ground may be stable and there may be reduce of the pore water pressure due to this drainage, and the effective stress may increase due to this drainage. Then we discuss the how this geosynthetic material also other types of function of the geosynthetic material, and what are these? These are we can use the geosynthetic material piping resistance also used for permeability, purpose and also used for the strengthening of and durability of the soil. And also the geosynthetic material used to control the erosion due to the draining or seepage of water. So different way we can use the geosynthetic material, and by also by different elements also we can use the geosynthetic material uh, to strengthen the slope. And you can see there there are three pictures are shown for, and there are three different way. Also, you can um, stable the ground. Now, so these are the application of this geosynthetic material. Most of the case, these geosynthetic material are used in the pavement or roads because it is very cheap, and the road construction needs very less time for, and there may be also needs to improve the subgrade material. So we use geosynthetic materials most of the cases to improve the road. So we use the generated subgrade material to improve the subgrade characteristic and properties also. And you can see that without the geosynthetic material, there may be bend on the pavement, and the pavement get damaged. And with geosynthetic material, the structure of the pavements or thickness of the pavement may contact with the ground, and the load can distribute it properly. So then we discuss the other applications as a reinforced base reinforcement. So we reinforce the soil with the geosynthetic material for the proper load distribution, and then we reduce the concentrated stress over one point, and it is distributed over the large point, and reduce the probability of damage, cracking, water ingress like that. So we also need to, due to this material, we also minimize the wave crack propagation below the pavement surface. So if we without the geosynthetic material, the crack which is developed at a depth may get propagated up to the surface, and the pavement surface may get damaged. And to stop this or to minimize this, we can use this geosynthetic material below the pavement surface. By this way, we can stop the propagation of crack. So by this way, we increase uh, the strength of the or durability of the pavement surface. So, and one figure also shown here thickness of the pavement layer and how we can use this centimeter in different way. This figure we can clearly clearly understandable, and at what portion and what layer we can use the geosynthetic material. And we can you can see that geosynthetic material used as a barrier, as a filtration, drainage, stiffening also, as a reinforcement material also, and a separator also we can use for this pavement purpose. Then also can you use the drainage purpose also for dewatening the subgrade. We can use this geosynthetic material, and also you see that by see that figure that one geosynthetic pipe, a prefabricated perforated pipe is here, which is collect the water and drain out or expel out the water from the slope as slope gets stable. And you can see that due to this arrangement the water table also get reduced, uh, uh, the what depth of water table will also get reduced. So one more. more pictures are given to stabilize the slope here. So like this way. So also we discussed the what are the different benefits to use the geosynthetic material. And we here discussed that we enhance the geotechnical engineering properties, including bearing capacity, structural capacity, shear strength, and deformation resistance, like that. And enhance the structural performance, spreading and distribution of the stress, improve the subgrade strength, and these are the many different benefits we can while using this geosynthetic material. Then now uh, uh, we also discuss the what are the different way we use the geosynthetic material and create some structures which is commonly civil engineering structure, like where we can commonly use this geosynthetic material, like mechanically stabilized wall, one of the retaining wall, one type of retaining wall where we can use the geosynthetic material, and here we use the geosynthetic material as a reinforcement material, so which increase the tensile strength of the ground and also stabilize the ground from the failure, different failure. So you see that uh, uh, and also discuss the different limitations and advantage of this mechanically stabilized wall, earth wall. So and also discuss the different types of failure. We discuss about the external failure, internal failure, the sliding failure, internal failure, local failure, compound failure, global and global failure also. So in external failure, discuss about the sliding, overturning, bearing capacity failure, and internal failure, we discuss the rupture, pull out, and connection failure. In local failure, we discuss the toppling and bulging, and compound failure, we discuss about the uh, we discuss about the partial slope failure or slip failure, and global failure we discuss about the some form of slope failure. So we discuss and also discuss the what are the forces act on this wall, tension strength act due to this failure, and how much this force are need to be addressed. We also discuss, and one schematic diagram also shows that, and load distribution also shown for this uh, uh, for periodic diagram shows of, and here we also show the different types of force acting on this mechanical stabilized earthen wall, and this for system is designed for this active earth pressure, which is given by the Rankine and Coulomb theory. um, and we also discuss the active earth pressure for this one, and one formula also we discuss. So by this formula, we can find out the active earth pressure for this type of retaining wall. So here also we show the different type of failure mechanism, failure surface for different type of material. When we use different type of material, when we use geosynthetic material, the surface is like this way. One wedge, a failure wedge is created, which is from zero at the uh, uh, which is connected from the toe to at the base the top slope. And when we use the metallic material like one steel rod or like that way, then the failure surface is constant at the top, and it gets reduced at the top. So these are the different way we use this material one for different types of material. Sorry, mechanical stabilized one for different types of material. And we discuss also Ki or active earth pressure for this soil like this way. Now we uh, and also discuss the what are the different types of factor of safety for different failure. For siding, we use the factor of safety greater than 1.5. For overturning, we use the factor of safety greater than 2. Sorry, 2. And for bearing capacity, we use the factor of safety greater than 2 to 2.5. And also for internal geosynthetic material, the rupture we use the factor of safety greater than 1.5. For pull out also factor of safety from greater than 1.5. For connection also factor of safety 1.5. And for overall failure mode, that is deep seated, factor of safety is greater than 1.3. For settlement, which is for different settle, which is greater than for project demand. And here also again one schematic diagram is shown for external stability and different types of force are acting, and we find the different factor of safety for this way. And by this formula we try to solve one problem today. And we need to design one retaining mechanically stabilized retaining wall or earthen wall by this formula, and we check whether this wall is safe, which I am going to design. And for this, we need to check the factor of safety. If the factor of safety is satisfy our required value, that is for sliding, the factor of safety is greater than 1.5. For overturning, factor of safety is greater than 2. Then we can say that this structure is safe to take the loads. And we can use this design in real field afterward. So now we discuss, and again here is the load distribution is shown at the base of the curve. One two type loads are shown here. One is bending moment, and another one is direct shear stress. Bending stick, direct shear stress. And also we find out the eccentricity of the load, and we need to also address the we also need to keep the eccentricity one marginal value, because if the eccentricity exceeds the tensile stress at the base will be increase. So we need to keep our design in this way that the eccentricity may limited one particular value which is safe for the tensile plane at the base. So now we start our today's discussion lessons. So please wait. I think my so now today we're going to discuss the mechanically stabilized earthen wall design parameter and procedure. And now we one by one discuss the design parameter and procedure of the mechanically stabilized uh, earthen wall. So I will discuss the procedure. So it is said that for local stability analysis, the possible local failure include toppling of the blocks above the uppermost reinforcement and bulging between the blocks when the modular blocks walls are constructed. The height of the blocks above the uppermost reinforcement and the spacing between the adjacent reinforcement layers should be less than the two times the block depth to avoid the local failure modes. The most modular blocks was the allowable mixable reinforcement spacing is 0.6 meter. So these are the some requirements which you need to address during the designing the mechanical stabilized earthen wall to save from getting to reduce the failure or to make it safe from the local failure. Then the compound and Google stability analysis with the analysis, the stability analysis of the compound and Google failure are the same as those for the reinforced flow. That means we need to stabilize in this for sliding, overturning, and for from the bearing capacity failure. Then consideration of the tire rate wall. So the tyrant mechanically stabilized wall may be used to reduce the required reinforcement tensile strength for the tall walls. And in addition to design of the individual wall stability, the overall stability should be checked using the slope stability method as shown in figure. So we can use the tire wall when the height of the wall is more, or we can when the wall height the wall is very tall. So we divide the wall in number of sections and we design one by one for this section. So we can see that you see that there is one wall. So step-like structure, the stair-like structure is created, or wall created when the height of the wall is very large. So we divide the wall in number of section and one by one we design this wall, and so we can see the step or stair-like structure is created by this way, and by this way. So, but when we need to check the overall safety, so we consider this not consider individually. We take the whole wall as at once and then check the safety of this wall, and these are we check the sliding, overturning, and also we check the bearing capacity. Like this way, we design the mechanical stability wall for tall. Uh, tall or large height with the help of the tirade walls. And these are the tirade walls. You can see this picture. So, so now we discuss the design parameter. So, performance of the mechanically stabilized walls depends on the many factors, and they are listed below. Geometry of the wall. For geometry, the wall height we use as a edge, top slope height we need to check, wall better angle we also need to check. Then top slope angle we consider, which is beta. Wall amendment depth also we consider, which is capital D. Then also we need to consider the properties of the reinforced field, whether it is capable to take the loads or not. So for this, we need to check the friction angle of the reinforced field. We need to write also the reinforced field. And also again, we need to check the properties of the retaining soil. For this, we need to check the friction angle of the retaining soil and unit also of the retained soil. Then, then we also need to check the properties of the foundation soil, where we check the cohesions, friction angle, unit weight, then properties of the top slope, unit weight, topsoil unit weight, then properties we need to check the properties of the reinforcement, that is length of the reinforcement, front anchorage length, that is L suffix AF, the rear anchorage length, that is L suffix AR, tributary. distance, that means spacing between the reinforcement, that is S suffix pi. Allowable tensor, sorry for that. Sorry. The I think why what I'm discussing, yes, allowable tensor strength, that is TA, pull out capacity. We need to check the pull out capacity such as PO. Also, we need to check the allowable connection strength, that is T suffix CA. And also, we need to check the structures. What are the structure slopes due to the slope of the top soil, top slope soil. And again, there is one schematic diagram is given for which is shown the different force or different reinforcement or material use in this session. Sorry. So we see that the top slope angle is beta, and then the fair surface angle is psi. Top slope surface unit is gamma s. And such as also shown the small p, height of the total height of the wall is h1, and top height of is ha suffix s. Like this way, different things shown in this figure. So now we discuss the quality of the reinforced field. What are the quality need to check during when use the geosynthetic material as a reinforcement and to create the mechanically stabilized earthen wall. So here it is said that the performance of the geosynthetic reinforced earth wall depend largely on selection of the reinforced field. According to the ISO 2012, the gradation for the backfill or the reinforced zone should be given as table. So here is the table. That means for ship size, one when the ship size is 102 mm, the material should be passing 100% material should be passing. And when the ship size is 0.4 to 5 mm, the percentage of passing should be 0 to 60%. And for when the ship size is 0.075 mm, the percentage of passing should be 15%. And for plasticity index, which is should not be greater than or exceeded 6. And these are the gradation we need to check use while check while using the material as a reinforced field. So then the selection of the poor quality backfill material is one of the reasons that cause failure of a geosynthetic or metallic reinforced artwork. An increase of fines in backfill result in poorer drainage and causing high excess for water pressure, which may result in wall failure. A decrease of friction angle of backfill increases the horizontal stress and reduces the pull-out capacity of geosynthetic or metallic reinforcement so that stronger and longer reinforcement are required. The pH value of the backfill should be checked and the accordingly a proper geosynthetic type can be selected based on the table. So these are the requirements we use while choosing the geosynthetic material, reinforced material to create the earthen wall, which is mechanically stabilized. So mechanically stabilized earthen wall. Now we need to check the pH limit for the backfill material when we use this as a geosynthetic reinforced material. So it is said that for polyester, which is in short it is written as PET, it should be the pH value should be in between 3 to 9. For polypropylene, which is in short it is written PP, and for high density polyethylene, which in short written is HDPE, the pH value should be greater than 3. Now we come to design procedure. So how we proceed while designing the reinforcement retaining wall. So it is said that the procedure commonly used in practice for the design retaining wall are given below. These are selection of the reinforced type. These are geosynthetic versus metallic reinforcement. Metallic reinforcement means the rod we use in the building. These are called metallic reinforcement. And geosynthetic, which are like grid, geotextile, these are called all of these called geosynthetic. Uh, and the wall facing also we need to select. Then we need to laying out reinforcement based on the minimum length and spacing requirements. Then we need to calculate the coefficient of lateral arc pressure for external and internal analysis. Then calculate the factor of safety against different types of failure mode like external failure, including sliding, overturning, and bearing failure. If any calculated factor of safety does not meet the performance requirement, modify the reinforcement length suitably or increase until all the requirements are met. So these are the requirements we need to check while designing the mechanic stabilized wall. Then also calculate the maximum tension in each reinforcement and then select uh, the grade of reinforcement to meet the strength requirement based on the desired factor of safety. Also check the maximum tension against the pull-out capacity. If the pull-out capacity is not sufficient, extend the length of the requirement. Check the maximum tension against the connection strength of the reinforcement. If the strength is not sufficient, change the connector or reinforcement type to reduce the vertical pressing of the reinforcement. Calculate the factor of safety against compound failures. If the factor of safety is not sufficient, extend the reinforcement and or increase the tensile strength of the reinforcement intersecting with the critical slip surface. Calculate the factor of safety against global failure. If the factor of safety against the global failure is not sufficient, improve the foundation soil by basal reinforcement or other ground improvement technique. So these are the procedure we need. Or this is the procedure we need to maintain while designing the reinforcement art wall. So now one design example is given. We need to solve this design example. So it is said that a vertical. This example. Now we try to solve or discuss this problem now. So the problem are said that a vertical geosynthetic reinforced earth wall is shown in below. Geosynthetic reinforced are equally placed. The foundation soil reinforced field and the retaining field have the same properties. So determine the factor of safety against the external failure. So the problem we designed this problem for this geosynthetic reinforcement retaining wall, and all the values are given here. There means the gamma is given is 20 kilonewton per pascal, kilonewton per meter cube. See, equation is given 0, 5. This internal fit angle is given 34 degree. See, allowable tensile strength is given 100 kilonewton per meter. Cohesion in reinforcement soil is given, factor is given, CI is given zero point 0.8, alpha is given 1.0, RC is given 1.0, then height of the wall is given 3.7, then base of the wall is given 3.9 meter, and also the slope of the top slope of this wall is given 1 vertical to 3 horizontal, and spacing between the reinforced geosynthetic material is given zero point 0.6 meter, and this by this all of by this different data we design this polymer. So now we try to solve this problem. So we can see this in figure. Sorry, in my slides, we can see that first we need to find out the active earth pressure coefficient. So for this, we use the formula 10 square 45 degree plus 5 by 2. So by this way, we uh, find out the active earth pressure coefficient, that is KAI is equal to the 0.283. Then we find out the height of the tributary area of the layer. So what are the height? So for layer 1, the height of the wire is tributary area is, it is given here, zero point 0.4 plus zero point 0.3 meter. And how it is came, for at the top layer, the spacing between this reinforcement is given as zero point 0.6. So we divide by 2 and we get zero point 0.3. And for the top layer, the spacing between the material and soil is given is zero point 0.4. So we add these two and get this for top layer. We get this, the height of the top layer is zero point 0.7. Now we find out the stress, tensile strength of this layer by this formula, that is half into Ka, the active aspect square gamma, into Sv or square plus Kai into P. P is the structure. So after putting all this value in this formula, we get the tensile strength at this layer is 3.96 kilonewton per Pascal or per meter square. So, and for finding out the surcharge, that is P, we need some geometry calculation. That means we need to calculate the pressure of the top slope or top slope soil. So by calculating this, we find out that pressure at the top soil is uh, 26 kilonewton. And in for safety, the lateral earth pressure we divide by 2 and we get the 30. And then again we need to design this, find out the tensile strength for the layer 2. And then the height of the for layer 2 is zero point 0.6 meter. And after putting all this value again, we find out the tensile strength at layer 2 is 5.6 kilonewton per liter. By this way, we find out the maximum tensile strength of each layer. But for this one, layer 1, layer 2, layer 3, layer 4, layer 5, layer 6. Then we find out the length of the reinforcement material. So, first for this we need to consider the failure surface. For failure surface, We know that for our design consideration, the failure surface should be at an angle of psi. And to find out this psi is equal to the 45 degree plus psi by 2. And after putting all this value, you will find out this the failure surface angle is 52 degree. And then we calculate the failure surface by this trigonometry, and we need to find out the active length or stable length, length of the reinforcement, reinforcement for each layer. That means for layer 1, we find out that is 1.3 2 meter. For layer 2, it is 1.7. Like this way, we find out for different layer. And And after that, we find out the total maximum pull out tensile strength or pull out force. For this, we already discussed this formula in previous classes. We use this formula, that is 2 into F star F uh, F star alpha RC sigma Z LA, where F star is equal to 0.6710 5. So after putting all this value, we find out the pull-out strength for each layer, for layer 1, layer 2, layer 3. Now, if after this, we find out the maximum standard strength for these geosynthetic reinforced material, also geosynthetic material. Then Then we also find out by our formula, given formula, we find out the maximum pull-out strength. By this tool, now we need to check whether this is safe or not. First, check the safety, or we find out the factor of safety by the total pull-out strength divided by the total maximum tensile strength. And by this way, we find out the factor of safety. And if the factor of safety is greater than 1.5 for each layer, then we can say this structure is safe to take the loads. And you can see that for each layer, the factor of safety is greater than 1.5. So by this way, you can see that say that this our design is safe and our calculation also safe. So this arrangement is also used in real field also by our designing. Now we need to check again the different others safety also. That means bearing capacity failure, safety against bearing capacity, safety against uh, overturning. So we for this we need to find out the different forces acting or on this failure wise. So find out the active earth pressure, horizontal active earth pressure, vertical active earth pressure. Then find out the weight of the returning wall, and then after that we put all this value in this formula and get the factor of safety against the uh, sliding. So which are given here that W1 plus W2 plus active earth pressure vertical pressure into whole into the 10 delta. 10 and delta is the angle between the soil and the reinforced material, and which is divided by the active earth pressure horizontal, that is sliding force. And we can get that our factority is come about 3.17, which is greater than 1.5, which is safe for sliding. Then we need to check whether it is safe for the overturning. For this, we need to find out the overturning moment, also find out the resisting moment. And we find out that overturning moment here it is active horizontal active earth pressure into 5 by 3. So by this way we find out, and also find out the resisting moment. After putting all this value to the factor of safety again overturning, we find out that the factor of safety is 6.7, which is much more greater than 1.5, and that means it is safe. Now we need to check the factor of safety again, bearing capacity failure. So for this, we need to find out the eccentricity, and by finding eccentricity, we need to conclude that uh, whether there is created or tensile stress or not at the base of the retaining wall. For this, we use the formula that is L by 2 minus mv, that is vertical moment, or sorry, mr minus md, that means resisting moment minus overturning moment, whole divided by the summation of the vertical force. And we can see that and this eccentricity should be less than L by 6 for whole the case for any type of the soil, because retaining wall, because if it is greater than L by 6, there may be developed tensile force at the base of the retaining wall, and which is maybe dangerous for to failure, because we know that the soil is not take, or soil is failed by this tensile force. So we need to our eccentricity should be in between less than L by 6. L is the length of the uh, base of the retaining wall. So after that, we need to check the bearing capacity failures. For this, first we find out the bearing capacity at the base. For this, we use the bearing capacity for Tarjaki bearing capacity formula, which is gamma half into gamma into uh, 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 b into nq. Here nq is given is sorry nb n gamma is given is 31.1. So, and then we find out the bearing capacity at base, and then we find out the safe bearing capacity at base, and which is divided by the factor of safety 2.5. After all this value we putting in this formula factor of safety against bearing capacity failure, to find out that it is greater than 2.5. So it is safe. So our design is safe for this real field also. We can see that. Say that. So up to this, we discuss the formula up to this. Now up to this we stop here for 5 minutes break. After that, I continue the next of the our lectures. So now we take 5 minutes break. Again we join here and discuss further lessons. So please keep in this line or session. Please stay on this session, and I will again join after 5 minutes. So now it is back. So again, welcome back to this class. Now we conclude our rest of the lectures. So up to this, we discuss the first discuss the previous class. What are we discussing in the previous class? And then we discuss the design procedure of the mechanical stabilizer earth wall, and then what are the requirements to select the good reinforcement material, fill material, and then we try to solve one problem also. One problem also we solve here or discuss. So now further we bring ahead. So we discuss the construction consequence of the uh, mechanically stabilized retaining uh, wall. So first we need to prepare the site preparation, then construction of the leveling pods, then erection of the facing, that is panels, modular blocks, wire brackets, baskets, then or cables. So now we one by one discussing these points. So first one is site preparation. So it includes large removal of large objects, that is trees, then leveling of the ground to a desired elevation, then removal of unsuitable materials like such as organic matters, vegetation, etc. If the foundation soil is too weak, adoption of any ground improvement method. So these are the site preparation. Uh, these are the points which is includes in the site preparation. Then come to leveling pads. So leveling pad is mostly unreinforced concrete, but sometimes made of gravel, are casted or placed on the foundation soil to support facing panels, modular blocks, wire basket, or gabion. Pads are typically 300 wide and 150 thick. Then installation of wall facing. The first row of facing panels need to be braced to maintain their stability and alignment. Upper facing panels are placed on and connected to lower panels after reinforcement and fill are placed. Modular blocks and gabions do not need any bracing. Then compaction of fill. Fill material is compacted, leveled and reached up to a bottommost level of the reinforced as designed. Placement of reinforcement. When the compacted field reaches the design level of a reinforcement, the reinforcement is placed in on the top of the field and connected to the facing. The reinforcement should be manually pulled straight to remove wrinkles before placement of next layer of the field. Then we discuss the quality control and assurance, and which is most important for our design because it is done during our construction, and based on this we need to check whether the construction is further going on or not, and whether it is up to the mark or not. So in quality control and assurance, we need to check the quality, gradation, pH value, and electrochemical properties of the backfill material, and the grades of the reinforcement and corrosion protection for metallic reinforcement only. Inspect precast panels or modular blocks for any damage and quality issues. Ensure the elevation and alignment of leveling pads. Ensure panels or blocks are erected or placed within the tolerance vertical and horizontal alignments. So these are the points we need to check or need to control during our construction of the retaining wall by the using of geosynthetic material as a reinforcement. Then we come again. There are few points in quality control. These are verify the density of the compacted field and its corresponding moisture content. Ensure the reinforcements are placed in a correct orientation. Inspect that the reinforcements are correctly connected to the panels or blocks. Ensure drainage system behind the wall face and within the reinforced field are properly installed. Now, up to this, we discuss the up to this slide we discuss the Up to this, we discuss the mechanically stabilized returning rod. Now we discuss the which is constructed by geosynthetic material. Now we discuss the geosynthetic using of geosynthetic in slope. What are the benefits and advantages while using the geosynthetic materials to stabilize the slope? So now we discuss one by one. So first we discuss the principle of the reinforced slope. So it is said that for cohesionless soil, when the slope angle is larger than the friction angle of the soil, a slip surface will develop and part of the slope will slide down. This slip surface divides the slope into an active zone and a stable zone. The basic principle of geosynthetic reinforced slope is that geosynthetic reinforcement prevents the soil mass in the active zone from sliding down by providing necessary tensile resistance and resisting moment through its anchorage in the stable soil. Now we discuss the types of reinforced slope. What are the different types of the reinforced slope? So it is said that geosynthetic reinforced slopes are mostly built with vegetative face and hard facing. The selection of the slope facing is often dependent on slope angle and the soil type, as suggested by Colin 1996. Colin, one of researchers, which is given some criteria for selection of the reinforcement material depending on the slope angle and the soil type. And we will discuss this in the coming slide. Then it is said that uh, geosynthetic reinforcement can be wrapped or not wrapped at the slope face. The wrapped space enables the geosynthetic reinforcement to have more pull-out resistance from the front and stabilize the soil exposed at the face. At a flatter slope angle less than 45 degrees, the facing provides the area of vegetation which protect the soil from being eroded. At a steeper slope angle greater than 45 degrees, the vegetation growth is difficult and significant soil erosion likely happen. Therefore, permanent erosion blankets or hard facing is used to protect soil particles from being eroded. Now we discuss the different types of facings, which is based on the slope face angle and soil type. So, and also based on the whether geosynthetics is wrapped or not. So first it is given when the slope angle is greater than 45 degree, all and for all soil types, and for not wrapped, geosynthetic is not wrapped. When the geosynthetic is not wrapped at face, then we use the vegetated phase, hard phase. For vegetative phase, not recommended anything. For hard phase, recommend the Gavion recommend. And when we use geosynthetic is wrapped at phase, for vegetative phase, we use sod, permanent erosion blanket with seeds. For hard phase, we use wild basket, stone, shotcrete. Shotcrete. Shotcrete means something concrete and like that. Then when the face angle is in between 35 degree to 45 degree, and also the soil material is clean sand, that is SP, and rounded gravel, this is GP, that means poorly graded sand and poorly graded gravel. When we use the not wrap phase, in vegetative phase, we do not recommend anything. For hard phase, we recommend gabions, soil cement, and salt. And when the geosynthetic is wrapped at phase, at vegetative phase, we use the permanent erosion blanket sheet, and we use at hard phase we use wire basket stone shortcut. When the angle phase angle is in between, slope angle is in between 35 degree or 45 degree, and the material is silt, no compressible silt, sandy silt, silty sand. Sorry for that. Mm, silty sand. Then for when geosynthetic material is not wrapped at phase, we as vegetative phase we use bioreinforcement, drainage, composite gabions. For hard phase we use soil cement, stone veneer, salt. And for geosynthetic material is wrapped at phase, we use for vegetative phase we use the permanent erosion blanket with seed, and for hard phase we use the wire basket stone short kit. Sorry. Hmm. I think a small break is given for water. I after just few seconds I will join again. Please wait. And continue again further. Then there are other types, that is when the face angle is in between 35 degree to 45 degree, and the material is clay sand, well graded sand, and well graded gravel, uh, and when the geosynthetic is not wrapped. For vegetative phase, temporary erosion blanket with seed or salt, permanent erosion mat with seed or salt we use. For hard phase, we use hard facing, not knitting. Then when the geosynthetic is wrapped at phase, for vegetative phase, geosynthetic generally not needed. For hard phase, geosynthetic wrap not needed. When the slope angle in between, there is one few typographical mistake, that is here it is given as 250. It is not like that. It is 25 degree or 35 degree. So the geosynthetic material phase angle is when in between 25 degree to 35 degree, and the soil type is for all. We for geosynthetic is not wrapped at phase. We for vegetative phase we use temporary erosion blanket with seed or soil, or also can use permanent erosion mat with seed or soil. For hard phase, we use hard facing. We not use anything. For uh, when geosynthetic is wrapped at phase, we use for vegetative we use geosynthetic wrapped. We do not use anything. We also not use anything in hard phases. So these are the classification or types or different facing for depending on the slope angle and soil type. Also depending on the vegetative phase or not, or hard phase or not, and also in geosynthetic material or rocked or not. Now we discuss now we discuss about the failure mode, different failure mode of the slope while using the geosynthetic material to stabilize the slope. So these failures are mostly similar to our which we taught in our soil dynamics, soil mechanics class about the slope failure, similar type like that, and also some failure are similar to the retaining walls also. So now we discuss one by one. So here it is said that geosynthetic reinforced slope have four possible failure modes: superficial failure, internal failure, compound failure, and global failure. In all these modes, there are an active soil wedge and a stable soil mass. The active soil wedge is above the slip surface, while the stable soil mass is below the slip surface. So here one schematic diagram is given for different type of failure modes. So we can see that for internal failure is happening due to the material, geomaterial, geosynthetic material, which geosynthetic material you use, whether it is uh, uh, come to uh, our requirement or not. Then superficial failure is happen at the face of the slope. Then compound failure, which is already we talked about the sliding, overturning, or base failure, like that, slope toe failure, like that. Global failure is also similar to sometimes similar to the compound failure, or we can say base failure or toe failure. We can see it. And there is two type of reinforcement also used. One is secondary reinforcement, which is in short length. Another one is primary reinforcement, which is quite in large length. Then now we discuss the design procedure or design step of the geosynthetic reinforced slope. So first we discuss the performance requirement. What are the different requirements while performing of the this reinforced slope. So first it is given that factor of safety against internal, superficial, compound, translational, and global failures under static loading should be greater than 1.3 to 1.5. The higher factor of safety should be used if the slope supports sensitive structures. Factor of safety against internal, superficial, compound, or global failure under seismic loading should be greater than 1.1. Uh, Post-construction settlement should be based on project requirements. Stability analysis satisfying the performance requirement. So these are the points which you need to consider while design of the uh, uh, geosynthetic reinforced slope for performance requirement. Now we discuss about the internal stability, which is based on the internal failure. So in internal stability, we analyze during the internal stability analyze, we assume the slip surface passing through geosynthetic reinforcement. The contribution of geosynthetic reinforcement is considered providing tensile resistance to the movement of the active soil. Geosynthetic reinforcement can have three different failure modes in soil. These are tensile rupture, pull out from stable soil, that is rear pull out, and pull out from face, that is front pull out. So we have three different failures or internal failures are given. um, Internal failure. Hello, 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 hello. I think it is clear. Again, I am checking. Hello, it is clear. So these are the three different failure for internal stability. So here three schematic diagram is given. So the first figure is given for the tensile rupture failure. That is when we use the geosynthetic material as a tensile reinforcement material as a reinforcement that may fail due to tensile force. Then second figure is given for the pull out from the stable soil. That is when we use the geosynthetic material that may be pull out from the stable soil. They, these are one type of failure that are one type of failure. Then the third one is for pull out from face. That means when we use this geosynthetic material as a reinforcement, they, that may be pull out from the active soil. So or from the face. So these are the three different failure mode used in internet stability. You need to consider address in internet stability. Now we find out the force acting on this uh, uh, reinforced soil. And to find out the pull out resistance, total pull out resistance, we use similar formula which we used at mechanically stabilized soil. So the pullout resistance of geosynthetic reinforcement can be estimated by the following unit, that is Pu is equal to 2 F star alpha suffix SC sigma Z dash LA RC, where F star is the pullout resistance factor commonly assumed as 10 phi or C10 phi, where Ci is the interaction fraction range between zero point 0.6 to 1 and 0.67 as a default value for the most application. And by this formula, also we one problem we discuss by this formula just today's class only. Then alpha suffix Sc is the scale effect correction factor to account for a nonlinear stress reduction over the embedded length in between zero point 0.6 to 1 for geosynthetic, and the default value is zero point 0.6 for the geotextile and zero point 0.8 for geoclinic. Sigma Z dash is the normal effective stress applied on the geosynthetic reinforcement. LA is the anchorage length of the geosynthetics material. RC is the percentage coverage of the reinforcement. So these are the affiliation of the terms, and uh, by this by these terms we can find out the total pull-out resistance. Then here it is one figure is shown for to stabilize the reinforced slope by layering. One layer up above one layer. Layer by layer, we stabilize this slope and form a geosynthetic reinforced slope. And you see that two area is given. One is territory area, which is without geosynthetic. And that means this is the area which is not covered by geosynthetic material. And another one is geosynthetic area, which is covered by the geosynthetic material. And the RC is the coverage ratio, which is the ratio is between the geosynthetic area to the tributary area. Then the contribution of the geosynthetic reinforcement to the stability of the reinforced slope is to provide a anchorage force to the active soil mass through the stable soil. The anchorage force is often considered providing additional resisting moment to the active soil. Factor of safety, the reinforced soil is thus given by factor of safety is equal to the resisting moment and plus the moment which is created by the geosynthetic reinforced material, and which is divided by the driving moment. And this driving moment is for created due to the soil weight and the surcharge. Here one uh, procedure is given, a schematic diagram also given to find out the factor of safety uh, for the reinforced slope. So it is said that when the reinforcement force for each layer is explicitly accounted for, the factor of safety for the reinforced slope can be expressed as given below, which is factor of safety, uh, normal factor of safety for this stable return sorry reinforced slope, then plus summation of the total force tensile force of each layer into y I, that is lever arm from a certain center of failure surface divided by the driving force, and this summation of the TAI into YI is the resisting moment. So up to this, our class of this ground improvement class is covered, and up to this also we covered the geosynthetic material, about the geosynthetic material and what are the different use or application of this geosynthetic material. So now we discuss the summary of our total classes, which I am going taking here, and also I am discussing the today's lectures again very shortly to clarify a few points again. So when we discussing this geosynthetic material, we discuss about the different function of the geosynthetic material. That means uh, how many ways we use this geosynthetic material to improve the ground. So we also discuss the reinforcement, filtration, separation, drainage, erosion control, and bearing and protection. We use these by this different way of the geosynthetic material. Then we also discuss what are the different challenges we need to address while in geotechnical engineering, while and why we use this ground improvement technique in our civil engineering purpose. So it is said that with the increasing demand on the urbanization, we need to venture to more challenging sites to build more houses, commercial buildings, high-rise office buildings, highways, railways, tunnels, art dams as suitable site with the favorable geotechnical condition is not available. So for this, we need to improve the ground, and for improvement, we need different techniques like mechanical stabilization, hydraulic stabilization, grouting, chemical stabilization, physical stabilization. Also use some geosynthetic material. By this way, we improve the ground. We discuss all these things in our lectures. Then here it is also we discuss the different type of problematic geomaterial, that is natural soft clay, silt, organic clay, loose sand, layers, and expensive soil. And also discuss the different types of field, reclaimed material, and solid waste. So, and to need uh, for improve the ground, we need different types of geotechnic, ground improvement technique, and most available methods are excavation and replacement. We already discussed these all the things: shallow densification, deep densification, rapid impact compaction, vibro compaction, pre-consolidation, grouting, chemical stabilization. All the things we discussed. Then how to select method, and for we know the different methods, but when and where we use this method we need to know. So to select this method we need to consider the type of the material we need to improve, which material, which type of material we need to improve, and also it is dependent on the depth of the improvement, and also it is dependent on the availability of the material and methods. So, and also we discuss the groundwater and flow through subsoil, and here we discuss the dewatering technique, pre-consolidation, routing, then drainage, pump in, pump out technique like that. Then we discuss the stability of slopes and carts, where we discuss the soil leaning, soil anchor, application of geosynthetic, and these are the methods we use when the we need to address the retaining wall and slope. And these are the books we use in our ground improvement techniques. So most commonly used here it is uh, Principle and Practice of the Ground Improvement by Jehan Willie. These are the most popular books we use in our lecture. So up to this, our lectures is completed. I'm again discussing today's lectures very briefly, or I can very briefly or summarize today's lectures very quickly, so we understand more. And also I discuss previous class again. Few points are remaining. I think no need. So in today's class, we discussed about the procedure, design procedure of the mechanical wire stabilized earth wall, and the design parameters also we discussed. Here first we discuss about the local stability analysis. So first I think I need some break. After that I concluded. I am taking water break. Please stay on the line. Now we discussing very briefly. Now we discussing very briefly our our today's class. So first we discussing the procedure, design parameter and procedure of the mechanically stable artwork. First we need to check the local stability. For this, it is said that the failure local failure includes the toppling of the blocks above the uppermost reinforcement and the bulging between the blocks when the modular blocks was constructed. The height of the blocks above the uppermost reinforcement and the spacing between the adjacent reinforcement layers should not be less than two times of the blocks that to avoid this local failure. The modular blocks was the allowable maximum reinforcement spacing should be point 6 meter. Then we're discussing the compound and group stability, where it is said that the stability analysis of the compound and group failures are the same as those for the reinforced slope. Then we discuss the consideration of the tirade wall. In tirade wall, mechanistically wall may be used to reduce the required reinforcement tensile strength for the tall wall. So we actually divide the tall wall into number of steps and with stair-like structure, and we can actually reduce the tensile strength of the soil. Wall. By this way, we also can reduce the material need of material that is used into the material. So in addition to design the individual wall stability, the overall stability should be checked using the slope stability method. And one figure also we can see that, and this is given by the Lex Sky and Hell 2004. So one figure of titled wall is given. It is like step-like structure, or we can say stair-like structure. Uh, Individually design, and then we add one by one layer, and by this way we can design the tall retaining wall. Or yes, tall retaining wall. Then we will discuss the design parameter of the mechanistic stabilized earthen walls, which is mostly different factor. It is depend on the geometry of the wall. It is also depend on the properties of the reinforced steel. It is also depend on the properties of the retained soil. Also depend on the properties of the foundation soil, properties of the top slope soil, reinforcement properties and characteristics, and one schematic diagram also given for different layer and different materials are used and different force also created, and the failure surface of this wedge is created at an angle of psi. Psi is equal to 45 degree plus 5 by 2. Then we discuss about the quality of the reinforced steel. I will discuss the performance of the geosynthetic earthen walls, and depending on the most of the selection of the reinforcement soil, and this is given on the gradation of the backfill material for different zone, and I also see that the poor quality of the backfill material is one of the reasons that cause failure of the geosynthetic and metallic reinforced earth walls. The increase of the fineness of backfill material also reduce the drainage properties and cause the higher excess pore water pressure, a decrease of friction angle. Mm. Decrease of the friction angle of the backfill material increase the uh, uh, proper drainage and causing the higher excess pore water pressure, which may result in the well failure. Then we also need to check the pH value of the backfill should be checked and accordingly for the different type of geosynthetic material. And for different gradation, for different gradation, we for the different sizes of material should be passing for different sheet. That is for sheet size is 102 mm. The passing should be 100%. For sheet size 0.425 mm, the passing should be in between 0 to 60. For sheet size 0.057, passing should be in between 0 to 15 percent. And for check the plasticity, we should be not greater than the 6. And also the pH for different materials should be need to check. That means polyester, the pH should be material should be pH in between 3 to 9. And for propylene and polypropylene and for high density polythene, the pH should be greater than 3. And we also discuss the design procedure, that is first selection of the reinforcement type, then the laying of the reinforcement base, then find out the coefficient of lateral earth pressure, and calculation of the factor of safety for different failure mode, and also calculate the maximum tensile strength, allowable bearing capacity, allowable tensile strength, maximum pull-out strength, and also need to check the maximum tension against the pull-out capacity. The also need to calculate the factor of safety against the compound failure. Also calculate the factor of safety against global failure. Then we discuss one problem or design one problem where we find out the layer by layer different forces or tensile forces and what are the maximum tensile forces created due to this arrangement. First we find out, and it is based on the active earth pressure coefficient, and after also it is depend on the vertical normal vertical pressure. So after we find out the layer by layer tensile force and also find out the maximum pull-out resistance uh, of this geosynthetic material for this layer by layer, and we check the whether it is safe or not by finding out the factor of safety. And it is find out that all the layers for tensile resistance, all the layers is greater than all the factor of safety is greater than 1.5 for all the layers, and that means it is safe. Then we need to check out the different failure modes for that is sliding, overturning, bearing capacity, tension creep. We need to check. So uh, and and all the cases we find out that it is more than the factor of safety is more than its required value. That means for sliding it is more than 1.5. For so overturning it is greater than 1.2 1 sorry 2, and for bearing capacity failure it is greater than 2.5. We also we find out everything. Then also we find out the eccentricity, and it should be less than L by 6. L is the length of the base, and it is also checked. That is and it is also safe. After that, we discuss the consequence of the construction. First, we discuss the site preparation. Then we discuss the construction of the leveling plate, and then we discuss the erection of facing, placement and construction of field, placement of reinforcement. So all the things we discuss. Then again, we discuss the form by uh, any other ground technique. Also, we discuss these points. That means control and assurance. That means during the construction, at the field, we need to check or control the quality of the reinforcement. So uh, we go through it, and it is said that we need to check the quality, gradation, page value, and electrochemical properties of the backfill material. Also inspect the precast panel. Also, then we also discuss the elevation alignment of the leveling pad, block and ensure the panel or blocks are erected or placed within the tolerance vertical and horizontal elements. And these are the others we discussed that the verify the density of compacted field and its corresponding moisture content. Also ensure the reinforcement place in a correct place orientation. Also inspect that the reinforcement are correctly connected to the panels or block. Ensure the drainage system behind the wall face and within the reinforced fields are properly installed. So then we discuss the reinforced slitting slope. First, we discuss the principle. In principle, we discuss the what are the why the failure is happening in the slope, and we find out that when the friction angle of the soil is greater than the slope angle, then sorry, when the slope angle is greater than the friction angle of the soil, then only the slip surface is created and failure happen. So and we also discussed the different types of reinforced soil based on the type of soil, slope angle, also based on the vegetative phase or not, or hard phase or not. So whether the geosynthetic is not wrapped or wrapped by this way, different the facings or different types of reinforced soil we created. After that, we discussed the different failure modes of the geosynthetic reinforced slope, and we find out that different surface failure, internal failure, compound failure, and global failure. And one schematic diagram also we discussed. Now, some consideration or requirement also we need to check while designing the reinforced slope, adjacent to the reinforced slope. And it is said that the global factor of safety should be greater than 1.1 and also in between the 1.3 to 1.5. And and then also we discuss the internal stability based on three failure modes, that is tensile rupture failure, then pull out from stable soil failure, that means rear pull out, and pull out from face failure, that is for front pull out. We discuss all the things and also discuss the finding out the total pull out resistance, that is 2 into F star alpha SC sigma dash Z LS. So all the thing I think all the thing I'm discussing on here. So now I need to conclude our session. So this is our last session as per our as per our geo as per our ground improvement class. But there is one extra class I am going to take. which is happening at Wednesday at 6 p.m. same time. And this class mostly based on the discussion about all the lectures, whatever taught in this ground improvement, and very precisely and to the point. I am discussing all of the ground improvement methods, and if needed, any 2 3 problem we will also discuss based on your assignment, also based on your exam purpose. I think this course is very easy to understand and also very easy to score in exam, and uh, nothing too hard in this course. So I think all of whatever I'm discussing, it is very much understandable to all. So I am again discussing this on Wednesday in my extra class. Please attend this class. Now I am uh, close our session. So, and best of luck for your exam. And I'm again saying that this course is very easy. Nothing very tough in this course. Very easy to understand. But you have to remember lot of things uh, only. So now I think I close my session. It is already 8:07. And also one important thing is that India won the match, today's match. So it is very happy moment for us. So I now conclude our session. So thank you everyone. We will see in the Wednesday again, which will be our last class. So thank you.